Hi everyone, welcome back to Math 111. This is Scott. Let's get started. So today's topic will be section 3.5, which has to do with transformations of functions. And here's the idea. The idea is we're going to take some basic functions, usually from our toolkit, and we're going to customize them for certain specific situations. So the idea is take a basic function, such as a toolkit function, which you'll remember from section 3.1. That's a list of functions whose graphs we know the appearance of. It includes the identity function, a constant function, the reciprocal function, square, square root, cube, cube root, things like that. So take a basic function, such as a toolkit function, and customize it. For a specific situation. Alright, so here are the ways we are going to be able to customize these. So these are the transformations that we're going to be able to employ. So first off, there are two main categories of transformations. There are what are called vertical and horizontal transformations. Vertical. So these affect the y values of the points on the graph. And we accomplish these by doing something to the outside of some previous formula. So they are accomplished by making a change on the outside of a formula. So basically, you can imagine a formula as being a little recipe for generating the output. And then if you want to change the output after that, whatever you do has to be done on the outside, on top of the original formula. Then the other side of things is horizontal. Horizontal transformations, these affect the x values of the points on the graph. And they are accomplished not by doing anything on the outside, but rather they have a different philosophy. They are accomplished by replacing the x from the original formula. With some modified expression. And as a note about horizontal transformations, they will almost always stab you in the back. You're never going to be able to predict what they're going to be. It's always going to be the opposite of what your common sense will tell you. So they tend to be the opposite of what one might have expected. Okay, so that's going to take some special handling, but we'll see. We'll see with examples and such how this plays out. But first off, let's start with the easy side of transformations, which is the vertical side, and let's discuss what it is we have to do on the outside of a formula in order to accomplish some of the basic vertical transformations. So, vertical shifts. So we can shift or translate a graph by, and this means moving it up or down, by taking the original formula and adding or subtracting something on the outside of that. So we can shift up or down by adding or subtracting some value on the outside of the formula. So for example, let's say that what we had was some basic graph like, I should say f of x equals absolute value of x. So that's a classic toolkit function. And absolute value looks like a v. V for value. Okay, so this is the original function that we're going to be subjecting to some vertical shifts. So shift up 2 units. So instead of just y being equal to f of x, it's going to be f of x plus 2. In other words, y is going to equal the absolute value of x all plus 2, and notice this plus 2 is happening outside of the absolute value bars. These absolute value bars are going to be the boundary between what's inside and what's outside. And any vertical change is going to be happening outside of them. Vertical changes are what happen outside of the boundaries of these 2 bars. Okay, so adding 2 is going to mean that all the y values are now 2 higher than what they used to be, which means we still have the same basic v shape. The only difference is that instead of the corner of the v being at the point 0, 0, now it's at the point 0, 2. Now, if we instead wanted to do something like shift down 3 units. Then what we'd have is y equals f of x minus 3. In other words, in this case, y equals absolute value of x minus 3. So it's going to again keep the same shape, the same V shape, but now the corner of the V is not going to be at the origin anymore, not going to be at the point 0, 0, but it's going to be at the point 0, negative 3. So this is how you accomplish a vertical shift. No matter what the formula is, you accomplish a vertical shift by adding or subtracting some value on the outside of the formula. So here we added 2, it moved it up. Here we subtracted 3, it moved it down. Nothing too controversial happening there. Now let's stay on the vertical side of things and discuss vertical stretches and compressions. So vertical stretches and compressions, and then along with those also reflections, come from doing this. So vertical stretches, compressions, and reflections. So these are all the same family of transformations, and the way they happen is instead of adding or subtracting, you multiply the formula by something. Multiply a formula by an outside factor Now, if that outside factor is negative, then that's going to mean a reflection. If it's positive, then that means it won't. If the factor is negative, the graph will be reflected. About the x-axis. In other words, that means it'll be turned upside down. So we would call that being reflected vertically. If not, then we look at whether the factor is making the graph taller or shorter. If the factor is greater than 1, the graph will be vertically stretched. And what that means is away from the x-axis. If, on the other hand, if the factor is between 0 and 1, the graph will be compressed. Vertically, and that means towards. That means towards the x-axis. So as an example, let's say we took something like f of x is equal to the absolute value of x again. But this time, for the absolute value of x, now we're going to make a careful note of some of the important points so that we'll be able to watch the stretches and such happen. So one thing that's important to know about the absolute value is that the slope of each of these segments is 1 and negative 1. So what that means is if it goes out 1, it also goes up 1. And that's also true in the negative direction. So if it goes left 1 from the origin, it'll go up 1, and if it goes right 1 from the origin, it'll also go up 1. So those will help us keep track of stretches and compressions. We need something to help us keep the scale consistent. So now, let's say what we had was something like this. If y equals 2 times f of x. So before we had f of x plus 2, but now what we have is 2 times f of x. What that's going to do is, because it's a factor, that means it's going to be either a stretch, a compression, or a reflection. Because it's positive, that means it's not a reflection. Because it's greater than 1, that means it's a stretch. Essentially, the y values are all getting doubled. It's getting amplified by a factor of 2. So the graph of this is going to look the same as far as the general behavior, but what's going to be different about it is that everything is going to be zooming away from the x-axis twice as fast. Every point is now going to be twice as far from the x-axis as it was before. All the y values will be doubled. So now if this is 1, then up here, that would be now 2. If that's negative 1, then that'll be also at 2. So this is a vertical stretch. By a factor of 2. Versus, on the other hand, if I had y equals 1/2 times f of x. So now, because we still have a positive factor, it's still not a reflection, but because it's less than 1, what that means is the y values are going to be dampened a little bit. They're going to be compressed. Rather than being stretched out from the x-axis, they're going to be smushed in towards it. So instead of having a slope of 1, it's only going to have a slope of 1/2. And over here, same thing, only negative 1/2. So now if this is 1, this is only going to be 1/2. And same thing for negative 1. So everything here about this is getting smushed down by a factor of 1/2. So it's a vertical compression. By a factor of 1/2. Now, if the factor in front had not been positive, then what would happen is that all of the y values would be switched to their opposite. And that would cause what's called a vertical reflection, or in other words, a reflection about the x-axis. So then as more example, if we have y equals just negative absolute value of x, then that is going to be a vertical reflection. And so all the y values are going to be the opposite of what they once were, from taking as our starting point the original basic function of absolute value. So now they're going to be going down to -1. And then one last one of these, let's say y equals -2 times the absolute value of x. So here we would have the vertical reflection and also a vertical stretch. Now it's important to note the difference between a vertical stretch and compression versus a vertical shift, and it's a question of whether the formula is getting multiplied by a factor or whether it's getting added or subtracted. So if there's a term being added or subtracted, then that's a shift up or down. If it's a multiplication by a factor, then that's a vertical stretch or compression. And if it's negative, then it's a reflection as well. So that's vertical. Now, let's talk about horizontal transformations. Horizontal shifts. So with horizontal transformations, everything happens by replacing x by something else. And to do a shift basically means that you're going to be giving the x's more or less a head start or perhaps a delay. So to shift a graph, replace x by x minus something or x plus something to give the whole graph a delay or head start. So x minus 3, so if x gets changed into that, if x gets changed into an x minus 3, you may, just looking at that, have suspected that this would be a shift to the left by 3 because it's subtracting, but this actually represents a 3-second delay. Which in other words means shift to the right. If the whole graph is getting delayed, shift right 3 units. So if the whole graph is getting shifted to the right 3 units, that means all of the values on the graph, their x coordinates, are on basically a 3-second delay. But if the x instead gets replaced by something like x plus 2, that would represent a 2 a 2-second head start. And what that means is that it's going to shift left 2 units. Now, what this would look like with our old friend the absolute value is as follows. Example. F of x equals the absolute value of x. So here, if we want to shift this, so once again, important thing for these problems is that the corner happens at 0, 0. So if we want to shift, let's say left 3 units, just as a random example. So we want to shift left 3 units. So that means it's easier to tell what the graph of that should look like than it is sometimes to go straight to the formula. So the graph means everything is happening 3 units to the left of where it used to be, which means there's been a 3-second head start. Which means that the x in the graph is all the x values in the formula are going to be replaced by an x plus 3. They're all 3 seconds further along than you thought they would have been at that point. So that means y is equal to f of x plus 3. Where there used to be an x, now there's going to be an x plus 3. In other words, y is equal to the absolute value of x plus 3. And notice now this is what's called an inside change because it's happening inside. So horizontal changes are inside the formula. So in where the x would be, that's where you'll see the horizontal changes. Now let's say we want to shift it to the right 1 unit. Let's say we want to shift right 1 unit. So then let's think about what that would look like. So the whole thing would have been 1 unit to the right, which means the whole thing is delayed by 1 second. So in other words, x has been replaced by x minus 1. So that means that y is equal to f of x minus 1. In other words, y is equal to, in this case, the absolute value of x minus 1. Now notice this is a very unusual transformation. It goes the opposite of what you think. Another way of thinking about this is we're changing the meaning of 0. Here, we are at what used to be 0 when x equals negative 3. Here, we are at what used to be 0 when x equals 1. But it's a tricky business with the horizontal shifts. They go the opposite of what you think. To go right, you subtract. To go left, you add. tricky business, tricky business. And the trickiness continues for stretches and compressions as well. So the stretches and compressions are just as tricky. And I guess while we're at it, and reflections. So horizontal stretches and compressions along with reflections. So the idea here is that now we replace x by a modified expression where x is multiplied by a factor. So x becomes, we could say, just bx. Now, if b is negative, there will be a horizontal reflection. And we say here this is about the y-axis. So in other words, the y-axis is the axis of the reflection. Everything becomes the mirror image. If b is not negative, then that's not true. If b is greater than 1. So just like with vertical stretches and compressions, 1 is the threshold, but now the conclusions are all backwards. So if b is greater than 1, then the graph has been sped up. This means that the graph will be horizontally compressed by a factor of 1 over whatever b is. So if b is, for example, 2, for example, if x gets replaced by 2x, then that means a compression, a horizontal compression, I should say. By 1/2. So 1 over b. And the reason for this is that if it gets sped up by a factor of 2, then that means everything takes 1 over 2, or 1/2, as long. And on the other hand, if b is, I shouldn't say less than 1, because then that might be confusing on negative things. If I say if b is between 0 and 1, then the graph is slowed down This means that the graph will be horizontally compressed. Horizontally stretched, I should say, horizontally stretched by a factor of 1 over b. So in both cases, whatever the factor is, it's going to be 1 over that. And that represents the actual effect. And for example, if we have x getting replaced by 1/2 x, that's going to be a horizontal stretch by a factor of 1 over 1/2, but the reciprocal of 1/2, which is what 1 over 1/2 is the same as what you get if you were to multiply the top and bottom of this each by 2. That would cancel down there, and what you get is going to just be 2 over 1, which just equals 2. So it's going twice as fast. Sorry, it's going half as fast, so everything takes twice as long, and the graph gets stretched out. Now this is all very questionable stuff, I'm sure. I'm sure you're having a hard time believing it or understanding it. So before we get into a lot of examples of this, I want to justify myself by looking quickly at some instances of this on Desmos. So I'm going to switch to the computer in just a second here to look at Desmos. So it's going to look on Desmos. So you start by just typing Desmos, and it's just going to be the first thing that comes up, and you just click and click and click, and then you can start graphing. Now, the easiest way to watch function transformations happen is if you just start by taking f of x equals, and if you're doing this on a phone, it will look very similar to the keypad that you've got here, and you can find the f by going to the letter side of things. And here, let's just take as an example graph, we'll just go with the absolute value, just to start with. Here you can do this either by going to the function screen, and you go to miscellaneous, and I guess it's not actually there. Oh, there it is. Oops, silly me. There it was. There it was the whole time. So you can do that one and do it that way, or if you're doing it on a keyboard, then it's easy. You can do shift and then on the and then backslash will give you the absolute value, or you can just type in ABS. But in any case, there is the original function, and now, so that's the original function. Now I'm going to take it off the screen so that I can look only at transformations of it. So let's look first at some vertical transformations. So the vertical transformations here can be such things as f of x plus 1. So there's our original function, but now it's been shifted up 1. Or minus 1. There it is, all minus 1. Now, look at what happens if there's a factor in front. So if it becomes 2f of x, then that stretches it away from the x-axis. If it's 1/2, then that compresses it towards the x-axis. Notice that now it takes twice as long to get that high. But now, if there's a negative in front, then the whole graph becomes the opposite. Now for the horizontal side of things, let's look at a horizontal shift. Now if I did f of x plus 1, at first you might, just looking at that, think that it's going to be moving it to the right. But in fact it moved it to the left, and the reason here is that basically you took the whole graph and you gave it a 1 second head start from what it had originally. Or you can also think of it as, what now would you have to plug into x in order to get what used to be a 0? Well, now you'd have to plug in a -1 to get a 0 in here. So that's moving it to the right. To move it to the left, you would subtract 1. Now for the horizontal compressions and stretches, it'll be better to look at that with a slight modification to this particular function. So what we're going to do here is very similar to what we did to define a piecewise function. We're going to just make it a partial version of this, and I'm just going to say -5 less than or equal to x, which is less than or equal to 5, and then colon. And what that does here is it gives you an abbreviated version of the function. So it only gives it from -5 to 5. So it's basically a piecewise function that only has one piece. Now, here, let's look at what happens if I change x to 2x. Now at first, when you think about that, it looks like to the naked eye what's going to happen when you multiply by 2 is that should be stretching it somehow. But watch what happens. So instead of stretching it, it's compressing it. Similarly, if I'd used a 3, that compresses it. Everything is now going 3 times as fast, so everything takes 1/3 as long. Now, what if instead what we had was 1/2 times x? So now, if we zoom out a little bit, the graph has been stretched out from the y-axis. It's had a horizontal stretch. So this was original, and 0.5, in other words 1/2. And if it were 1/3, it would be stretched out even more. Now if it were negative here, you can't actually tell, because this horizontal reflection didn't actually affect the overall shape of it because it was symmetric about the x and y. But let's make it a function that's not quite so symmetrical. And here you're going to have to take my word for it. This is a different category of function, but I just want to have something to actually no, let's just go with the square root. That's a famous one from our toolkit. So I'm going to take the square root, take that one off the screen. I'm going to cut it off at x being 5, and we're going to go with square root of x. So okay, here's the original from the toolkit. We know it, we love it, square root. Now, here's what's going to happen if I change it to a -x. So, original, negative. Original, negative. Original, negative. So it's all pointing the other direction. Similarly, if I were to multiply it by 2, that compresses it horizontally, and if that were to be instead a -2, it'll be going the other way. Three compresses it horizontally, -3 puts it the other way. 1/2, or in other words 0.5, and that's a stretch. But then you make it a negative, and it goes the other way. So that's just a demonstration of these basic function transformations, each happening. Okay, now let's look at how we can combine multiple transformations to the same function. So combining transformations. So one way this can happen is that you have perhaps one horizontal and one vertical transformation. So vertical and horizontal transformations these are independent of each other, meaning you can basically do them in any order or at the same time. So for example, if I had something like y equals f of x minus 2 minus 3, then I can think of this as just being two separate things. So here is the boundary between the inside and the outside. And so everything inside here is horizontal, and everything outside is vertical. Now the horizontal transformation is that x has been shifted by 2, and because it is a subtraction, that means it's a delay by 2. So this is going to the right. Two. Whereas vertically speaking, all the y values have been moved down 3. Down 3. And there's no interference between the two categories of transformation. They all happen basically independently of each other. They're in their own little universes. What gets hard about combining transformations is if you have more than one within each category. So let's say that we had 2 vertical transformations. So if written in the form y equals a times f of x plus, and then let's say k, then the important thing to know is that if it's written in this form, then the a happens first and the k happens second. We work our way from the inside out, standard order of operations. So first, I should say vertical stretch or compression, or maybe reflection if it's negative, by A, and then secondly, a vertical shift by the amount of K. So A is a factor, K is an amount. And on the other hand, if there are 2 horizontal transformations, then if they are written in the order written in the form y equals f of, now say bx, say bx plus h. Actually, I'm gonna switch the notation here. Switch to what is kind of the standard notation. Y equals f of bx minus h. Then if that's what we have, first shift by h. Second, compress or stretch by 1 over b. Or reflect. Okay, let's have a look at what these can all appear as. So as an example, first off, maybe we might just want to describe. Describe the transformations. And maybe what we have is something like, first off, y equals f of 2x minus 3. So we can have a couple of transformations going on here. We have a 2 on the x, and we have a subtraction of 3. So first off, on the horizontal side of things, this is the boundary once again between the inside and the outside. This is where the input is changed, and outside of those parentheses is where the output is changed. So here, horizontally, what we're talking about is a multiplication by a factor. So that's going to be speeding up or slowing down the graph, which is going to be stretching or compressing it. And because it's being sped up, it's going to be compressed. Compress by a factor of 1/2. So it's going in, like that. Then as far as the vertical side of things, we are just moving it down 3. So just straight up, downward shift. What if, on the other hand, what we had was 2 f of x minus 3? Well, now that 2 is no longer within these parentheses, it's on the outside, which means it's now a vertical transformation. So vertically speaking, we have, first off, stretched by a factor of 2. And second off, it's going down 3. No horizontal transformations are in play here. Now as a third example, let's say what we had was f of 2x minus 3. So now everything is happening inside these parentheses, and so we have only horizontal games being played here. So we are going to have to work our way from the outside in. Because horizontal transformations are backwards in every way, and because the way they happen is that they replace the x by something else, we are going to have to deal with the fact that there is first a shift, and the shift happens to the right 3 units because it's a subtraction. And then secondly, there's a compression by 1/2. Now, let's see what any of this would look like if we were talking about one of our familiar toolkit functions. So as an example, let's say we wanted to sketch the following. Let's say what we had was something like this. Y equals x plus 2 squared minus 3. So we'd have to figure out which of the toolkits we're talking about here and what has happened horizontally and what has happened vertically. So the toolkit function that we're talking about here, the basic graph, is going to be just x squared, just the quadratic, just the square. So then, thinking about that, everything that is inside the square, this is all going to be horizontal, and this is all going to be vertical. So horizontally speaking, x has become x plus 2, which means that what we have is a head start of 2 units for the graph, which means the graph is going to be going to the left 2 units. Vertically speaking, what we've got is a shift down 3 units. So we're taking our old friend x squared, which looks like this, and we're going to give it those 2 shifts. So instead of the vertex being at the origin, it's going to be left 2 units. And instead of it being at a y value of 0, it's going to be down 3 units. Other than that, though, the graph is still the same old parabola. And the important thing about parabola is that 1 squared is 1. So that means that that'll help us set the pace of the parabola here. So it should be going up 1 as it goes to the right 1, and then after that it gets a little bit steeper. So there is the new graph, shifted to the left 2 units and down 3. Now let's consider our y equals negative absolute value x. Let's make it x plus 1 plus 1. Okay, let's think about the transformations that are happening here. So in here, these are the horizontal. Outside are the vertical. So horizontally speaking, we're talking about only this part. So x is going to be replaced by x plus 1, which means it's got a head start of 1 unit, which means it's going to the left 1. And that's the only horizontal transformation. Left 1 unit. As for the vertical side of things, we've got 2 things going on. We've got, first off, a vertical reflection. So the whole graph should be upside down. And second off, we've got a shift up 1 unit. So if the original graph is absolute value, then we're now talking about a version of the absolute value where the corner is not going to be happening at 0, 0, but at -1, 1. And importantly also, it is upside down. So instead of being a V, it's going to be an upside down V. So this is the general way you go about this. So problems will ask you to use the transformations to graph some version of your old toolkit friends. Now, the flip side of this situation can be find a formula. For the following. And maybe what we have is something like this. Maybe what we have is a graph of this sort. Let's say that's 2. And furthermore, just to be extra clear about things, let's say for a little bit of pace setting to make sure there hasn't been any kind of vertical or horizontal stretching or compressing, we go left 1, it goes up 1. Okay, so first off, you think about your catalog of known functions and you try to identify which one this matches. So it looks to be the square root. But basic square root of x goes like this. So we have to figure out what has happened to this compared with how it was supposed to have been. So the two transformations that appear to have happened have been, first off, there appears to have been a horizontal reflection. It was going right, now it's going left. Secondly, there appears to be a vertical shift up 2. So then, the new function. It's going to be y equals, and it is the absolute value of, not x anymore, but negative x. And then outside of the square root, which is the territory of vertical transformations, it goes up 2, so it's going to be plus 2. Now, another area of problem that you're going to have to do is you will be given a recipe for a sequence of transformations that you're going to have to perform. And the way these are going to look is as follows. Produce a formula for the following. And the way this is going to work is you'll be given an original function and then some transformations. The graph of f of x equals x squared is horizontally compressed by a factor of 1/3, then shifted left 2 units and down 1. Okay. So here's the approach for things like this. So the approach is you have to do it in steps. So do the transformations in stages. Build new vertical transforms on the outside of the formula, and then for horizontal transformations we build new horizontal transforms by replacing the x at the previous stage by the appropriate new expression. So back to the example, we start with f of x equals x squared. And now we need to make a formula that is now going to be this compressed 1, horizontally compressed by a factor of 1/3. Well, the way you do a factor of 1/3 is that you take what was the original formula and you replace every x by 3x. So that means you're going to have 3x all squared. And here now we can, if we want, we can simplify this out a little bit and make it just 9x squared. So this is our new formula as of stage 1. Stage 2, we are supposed to now shift it. We're now supposed to shift it to the left 2 units. And down 1. And these, one is vertical, one is horizontal, so these can be thought of as being totally separate from each other. So we take where we were as of as of now, and we replace the x by x, and to move it to the left 2 units, we do x plus 2. So it's going to be 9 times x plus 2, all squared, all within the square here, and then minus 1. So if we want to call the new function g, which is what the exercises will instruct you to do, g of x is equal to, it's now going to be 9 times x plus 2 squared, all minus 1. So the way we build the transformations is by taking whatever the original formula was and then changing what needed to be changed. If it's a vertical transformation, you just make the changes on the outside. If it's a horizontal transformation, you change it by replacing x by something else. All right. Now, let's, at this point, discuss the final topic of this section, which is even and odd functions. Even and odd functions. So first off, even functions. So a function has what is called even symmetry if it is symmetric about the y-axis. So what this looks like basically is something like this. So you can have a function and it might look weird. Might be going up and then going down like so. But then whatever it's doing on the other side will exactly line up. So the things on the left and the things on the right will always match each other. So if they have opposite x values, that will lead to them having the same y values. So what this means as far as a formula, in the formula, what this means is that if I were to take x and replace it by negative x, then that would be the same as just regular x. So change x to its opposite, and the output won't change. So that's what it means to be an even function. Now to be an odd function, that means that you have odd symmetry. Has odd symmetry if Now you might think if even was symmetric about the y-axis, maybe this will be symmetric about the x-axis, but it's not quite that. It is symmetric about the origin. And what that means is that it looks like this. So if this side goes up and then down like that, then on this side, what you see is the opposite. So right here versus right here, these have opposite x's. And those lead to opposite y values. So opposite x values lead to opposite y values. Now, as far as the formula goes, it's going to look a lot like this, except that the punchline will be different. So formula in the formula, f of negative x is going to be negative f of x. In other words, if we change x to its opposite, the output will be opposite. Now, making use of this formulaically is a matter of doing the following. So determining whether a formula represents an even function, odd function, or neither. Here's the procedure. So here, here's the procedure. Step one. Well, both cases here involved f of negative x. So step one, change x to negative x. Then, simplify. Now, the conclusion that you draw depends on how this simplifies down. If the result is the same as f of x, in other words, the original, then even. If the result is the same as negative f of x. So in other words, the original, but with a negative pulled out to the very front. Then odd. And if neither, then neither. Now let's give this a try. So let's try this with a few first of the toolkit functions and see where that takes us. Determine. Whether the following are even, odd, or neither. A. Well, let's start with some of our best friends from the world of the toolkit. F of x equals x squared. Famous. Well then, let's think about how this will go. X becomes negative x, and then we have to see how that shakes out. So f of negative x. Well, that's just going to be negative x all squared. But when you square something, it doesn't remember whether what you started with was positive or negative. So the square of the opposite of x is the same as just actually the square of regular x. And that's just the exact same thing as the original function. Which means, therefore, this is by the way an abbreviation for therefore. Very common, very useful. Therefore, f of x is even. B. Take f of x equals x cubed. We start the same way, change x to negative x. And it's important, the distinction between a negative raised to an even power and a negative raised to an odd power, in that if it's raised to an odd power, negatives will stay negative and positives will stay positive. So this is actually the same as if it weren't even in the parentheses in the first place. Negatives will stay negative, positives will stay positive. You can just basically pull it out. And so this is the same thing as the opposite of the original function, which means therefore f of x is odd. Now let's go with the reciprocal function. So what's it going to mean if we change an x to a negative x here? Well, 1 divided by negative x. But if you divide by a negative, that makes a negative result. So this is the same thing as just negative 1 over x. Which means that this is the same as the opposite of the original f of x, which means therefore f of x is odd. Now let's look at what would happen. Let's go beyond the toolkit and look at things that are made up of pieces that are from the toolkit. Let's say f of x is equal to something like x squared minus x plus 1. So the step here is the same. You just take an x and you replace it by negative x. And so everywhere there used to be an x, there shall now be a negative x. We are careful with our parentheses whenever there's something being squared or anything else that's happening. So that's what we get if we just do a find and replace and make every x negative x. But here what we have as actually stated up there, is just x squared. Over here, what we have is plus x, and then plus 1. So this, if we compare it with the original function, is not exactly the same as the original function, but it's also not exactly the opposite of the original function. This term and this term are the same, this term is the opposite. So this is not the same as f of x, but it's also not the same as negative f of x. Therefore, f of x is neither even nor odd. And this is the main way the functions that are neither will come about, is that there'll be combinations of functions, part of which will be even, part of which will be odd. Let's see, let's take something like this. E. F of x is equal to x minus 1 over x. So now we once again start the game the same way. The opening move is always make x negative x and see what happens. So it's going to be a negative x minus 1 over negative x. Now if we look at it, what happens here, that's going to be the same as minus negative 1 over x. In other words, negative x plus 1 over x. Now you look at this and you look at the original and you notice that it's definitely not the same, but actually term by term it's completely the opposite. So this means if I were to pull a negative out, I would end up with negative x minus 1 over x, which is the same thing as just negative f of x. So the opposite of the original. So therefore, odd. Now let's take as one last example f of x equals x plus 1 over x minus 1. F of negative x. So once again, our first move here is totally typecast. We have no option but making every x the opposite and seeing what happens. So negative x plus 1 over negative x minus 1. Now here, this is a different case. This is a different case from what we had before. When we had a fraction before, we were able to pull the negative out to the front because the negative belonged to the entire numerator or the entire denominator. But this is not the same thing. The negative is only on the x. It's not on the it's not on both terms. So this is not the same as f of x, and it's also not the same as negative f of x. And it's sometimes a little bit hard to tell when you can pull the negative out, but basically, to pull the negative out, it would have to be something that would be where it would be helpful to take it out of both terms, pull it all the way out, and then what you're left behind should be equal to the original expression. So if I were to pull a negative out of this, then that would become x plus 1 in the bottom, not x minus 1. And similarly, if I were to pull a negative out of this, then that would make that minus 1, not plus 1. So it's not going to be, so we're not going to be able to do anything profitable with these negatives, and also they don't cancel each other because they're not factors of the entire top or the entire bottom. So it's not the same as the original function. It's also not the same as the opposite of the original function. And so therefore, neither even nor odd. Okay, now that, I believe, covers that. So I will see you next time for another episode of Math 111. Until then, bye.